Hello everyone, this is Lakshmi. Welcome to my channel Lakshmi Lucky. Okay, today we'll discuss the Riemann integration, very important theorem, necessary and sufficient condition. Okay, so it is very important theorem in field analysis in this Riemann integration. So the statement has given a bounded function f is integrable on closed interval a comma b if and only if for each epsilon is greater than 0 the corresponds a delta is greater than 0 such that for every partition p of closed interval a comma b with norm p is less than delta UFP minus LFP is less than epsilon has given. Okay, this is the statement one. So here necessary condition we have as well as sufficient condition is there because here given if and only if condition. Okay ma? So in the first case what has given f is nothing but bounded as well as it is integrable on this interval a comma b. Okay, so first you should consider this condition, then we need to prove UFP minus LFP is less than epsilon. Whenever here given epsilon is greater than 0, there corresponds there exists a delta is greater than 0 such that it should be exist a partition P on closed interval a comma b. Okay, and as well as here length of the partition is nothing but less than delta has given. Okay, in the second case we need to consider this one second part, have to prove the given bounded function is nothing but integrable. Okay, we'll prove one by one. So in the first case I am taking necessary condition. Necessary condition, let f is nothing but I am taking integrable on closed interval a comma b. Okay, so integrable means what I said, it should be satisfies upper Riemann sum, upper Riemann integrable as well as lower Riemann integrable. Is it right ma? That is a bar to b f of x dx. It should be equal to integral a to b bar f of x dx. It should be is equal to common term a to b f of x dx. So here integrable they are already has given. So that's what we need to take this condition. Okay, and given epsilon is greater than 0, it is very smallest positive real number ma. And by Darboux theorem, it should be existed. This statement ma, Darboux theorem statement. There exists delta is greater than 0 such that for each partition P of closed interval a comma b and its length is nothing but delta. Delta is also smallest positive real number. It is depends on epsilon. Okay, and UFP is less than integral a to b bar f of x dx plus epsilon by 2. It is nothing but equal to I am taking instead of upper Riemann integrable a to b bar f of x dx I am taking a to b f of x dx plus epsilon by 2 as it is ma. A to b f of x dx why we are taking ma? Because it is already given integrable condition, the given function, right no? So that's what a bar to b f of x dx, a to b bar f of x dx equal to what is there? A to b f of x dx, right no? So that's what we need to take instead of this. I am taking a to b f of x dx plus epsilon by 2 as it is you should write. Okay, this is make this equation 1. And second case lower Riemann sum, that is LFP, it is greater than integral a bar to b f of x dx minus epsilon by 2 you should take my here, and it is nothing but also instead of a bar to b f of x dx a to b f of x dx. Similarly from this condition only minus epsilon by 2 as it is ma. Again here LFP is greater than is there is equal to a to b f of x dx minus epsilon by 2. Greater than ఉంది కాబట్టి less than case చేసుకోవాలనుకుంటే we need to take on both sides negative term. Okay, so negative should apply on both sides. Minus of LFP is less than, relation will be changed because we are taking on both sides negative no, so its relation will be changed. Greater than should becomes less than. Okay, minus LFP is less than minus integral a to b f of x dx plus epsilon by 2 minus because here minus is there, it should becomes positive, right mama? So make this equation 2. So from these two equations you should add. Okay, adding equations 1 and 2, then we have on the left hand side terms, left hand side only you should add, and the right hand side terms right side only will add ma. On the left hand side from the equation what is there? UFP, and here on the left hand side minus LFP is there. Adding UFP minus LFP is less than what is the condition is there? Here integral a to b f of x dx plus epsilon by 2, right here integral a to b f of x dx plus epsilon by 2 minus integral a to b from the second equation ma f of x dx plus epsilon by 2 is there. So here minus term plus term should get cancelled, is it right? So what are the remaining terms on the right hand side? Epsilon by 2 plus epsilon by 2, 2 epsilon by 2, here 2 also gets cancelled ma, remaining is epsilon. So therefore here on the left hand side what is there? UFP minus LFP. On the right hand side we have epsilon. So what is the relation in between these two? Less than is there, right now? So therefore here UFP minus LFP is less than epsilon. Okay, for each here partition P on closed interval a comma b with the length of the interval, length of the partition P is nothing but less than delta. This is the necessary condition. Okay, we'll see now sufficient condition. Now necessary condition completed. No, now we'll discuss ma sufficient condition from this statement. So in the first necessary condition, first condition f is integrable, then we proved ma UFP minus LFP is less than epsilon. Right now we are taking UFP minus LFP is less than epsilon whenever it should be existed delta is greater than 0 such that partition P of closed interval a comma b with the norm P is less than delta. Okay, and here let epsilon is greater than 0 for each partition P of closed interval a comma b with the norm P is less than delta, means norm is nothing but length of the partition P. Okay, it is less than delta, and here we are considering second condition, no, UFP minus LFP is less than what is there? Epsilon. So here delta always depends on epsilon only ma. So also for any partition P you should take, for any partition it should be exist this condition ma. LFP means lower Riemann sum, always less than or equal to lower Riemann integrable. Lower Riemann sum is always less than or equal to lower Riemann integrable a bar to b f of x dx. Lower Riemann integrable always less than or equal to upper Riemann integrable, right no ma? A to b bar f of x dx. Okay, and it is less than or equal to UFP. UFP is upper Riemann sum. Okay, so here I am taking these left side terms. These left side terms I am taking on the right hand side. Integral a to b bar f of x dx. We should bring this side ma, this term integral a bar to b f of x dx. So here it should become a to b bar f of x dx as it is, minus here a bar to b f of x dx, it should become negative ma, a bar to b f of x dx less than or equal to, right side what is there? UFP minus here LFP is there na, that LFP it should become negative ma, minus LFP, and here epsilon is nothing but by from the equation 3. Okay, so UFP minus LFP what is there here? Less than epsilon. So that's what ma, this total is less than epsilon means on the left side condition integral a to b bar f of x dx minus integral a bar to b f of x dx is nothing but less than epsilon only, because epsilon is nothing but here positive greater than 0, that is arbitrary. Okay, that means ma, it should, this total term is nothing but converges to 0, that should be equal to 0. Converges to 0 means, so a to b bar f of x dx minus a bar to b f of x dx should be equal to 0. So it should be equal to 0 means what ma, this negative term should becomes positive on the right hand side. So a to b bar f of x dx is nothing but equal to a bar to b f of x dx. This condition is nothing but what? Integrable. So given function is nothing but what we can take? F is integrable. So therefore every bounded function f is nothing but integrable when it should be satisfies a to b bar f of x dx is nothing but equal to a bar to b f of x dx. So this is the proof of necessary and sufficient condition theorem. Okay, very important theorem. Note this theorem and prepare well, and Yeah.